Chapter 10 has 3 sections. So we have 3 sections left for all of Calculus BC. 10.1 and 10.2 are about functions that you can make where you describe the behavior in the x direction differently from the behavior in the y direction. So we've already talked a little bit back in chapter 3 about parametrically defined functions. If you can write a separate function for the x and the y behavior in terms of a third variable, which is usually t, we can describe curves that aren't necessarily functions the way we're used to functions passing the vertical line test. But we can still do calculus on them. So this is a review question from chapter 3. If you... Oh, and just remember here, so I wrote this formula in, but where does it come from? If you have 2 functions, x and y, are both functions of t, and you want to find dy dx, what you do is you use the chain rule, right? So the derivative of y with respect to t is the derivative of y with respect to x times the derivative of x with respect to t. The problem is, it's this and this that we usually know, and this that we're trying to find. So I'm going to isolate that equation for dy dx, and I get dy dt over dx dt equals dy dx. So that's an application of the chain rule of implicit differentiation, and then I had to resolve for a different variable. So that's what we're going to do. We wouldn't ever be asked to go through that process there, but you need to know how to find the slope of a curve defined parametrically, and this is how to do it. So here I go. If I can think of this is the dy dx is in fact the slope of the curve, even though this curve is drawn differently than I might be used to drawing curves that are given as y as a function of x. So if x is secant of t and y is tangent of t, find the tangent to the curve at the time when t equals pi over 4. So tangent meaning tangent line equation. I'm going to need an ordered pair, an x and a y. I'm going to need a dy dx to give me my slope. And I'm going to use that information to write point slope form for the equation of a line. Find x when t equals pi over 4. This is me trying to find the ordered pair, x1, y1. I'm going to use a point slope formula. So what do we have? Secant, I could label it, x of pi over 4 is going to be the secant of t, which is secant of pi over 4. Secant is 1 over cosine. The cosine of pi over 4 is 1 over radical 2. So the secant of pi over 4 is radical 2. Step 2, I'm going to find the y coordinate. I have y is tangent of t, so I'm going to say y of pi over 4 equals tangent of pi over 4, which I hope you know and love as 1. Okay, so I know my ordered pair now, and I'm going to find my slope. Essentially, to do that, I'm going to need both the derivative of y with respect to t and the derivative of x with respect to t. dy dt is, derivative of tangent is secant squared of t. I'm going to call that dy dt. That's me taking the derivative of y with respect to t, and y is a function of t, so there's nothing complicated there. I need now dx dt, the derivative with respect to derivative with respect to t of secant of t, dx dt. The derivative of secant is secant t tangent t. Okay, so hopefully a little review. Now I'm going to write an expression for dy dx, and I know that's dy dt divided by dx dt. I notice here that one of my secant factors is going to cancel out top and bottom, so I'm going to write secant of t over tangent t. Secant is 1 over cosine divided by sine over cosine. Well, it does simplify further, huh? Alright, so let's... All right, so I was finding dy dx. I found that that's going to be secant of t divided by tangent t, but I noticed that that simplifies further, which obviously would not be required to do on the free response section. But my cosines here are going to cancel. And my dy dx is 1 over sine of t. That's another way of saying cosecant t. 1 over sine of t. Step 6, find the value of dy dx when t equals 4. So sine, t equals pi over 4. Sine of pi over 4 is 1 over radical 2. So 1 over radical 2 is radical 2. That's helpful because that's the slope of my tangent line. Use the slope I got. Oh, there was a point where I had labeled those as letters, and now I wrote them as steps, but I didn't fix this part. So use the slope I got and the y and x coordinates I got to write the equation of the tangent line. So y minus y1 equals the slope times x minus x1. You could simplify that as much as you care to, or not. But just remember that the big deal here is if I want to find the derivative of y with respect to x, and neither y nor x is, well, and both y and x are written as functions of t, I have to apply the chain rule and find dy dt divided by dx dt. Okay, that's great. That helps me find the slope of a curve because I know that's what a derivative is good for. Dy dx, the slope. What if I want to find a point of inflection? What if I want to find something about concavity? I can do that. And this is what's new in 10.1. Okay, so now I can find the second derivative of a curve defined parametrically. This doesn't quite work the way you might guess it would, so pay close attention here. The expression we found in that last example, dy dx, that's the derivative of y with respect to x. The thing was, neither y nor x was written as a function of the other, so we had to take the derivative with respect to this third variable and require the use of the chain rule. So that expression we have, dy dx, now I want to take the derivative of that with respect to x again, but dy dx isn't a function of x, it's a function of t again. So I'm going to take the derivative with respect to time, because that's the variable in dy dx, and then I have to multiply by dt dx. Well, dt dx is a little weird here because we have x as a function of t. So dt dx is the same as the reciprocal of dx dt. So we, instead of multiplying by dt dx, which we could find, but it would take a lot of extra algebra. There's my whiteboard. Just notice that instead I'm going to divide by dx dt. And you already found dx dt. Well, you were finding dy dx in the first place. So watch this one, and then there's another example in your textbook if you feel like you want to see it again, and I'm going to let you try this example, the next example, on your own. Okay, so find the second derivative of y with respect to x, a function that could tell you about the concavity or the points of inflection of the path of this curve. As a function of t, if x is t minus t squared and y is t minus t cubed. So my first step is to find dy dx, which is dy dt divided by dx dt. Well, dy dt is 1 minus 3t squared. And dx dt is 1 minus 2t. Piece of cake, right? Okay, now to find the derivative of dy dx, I need to take the derivative with respect to the variable that is there. So where do I want to write that? Okay, I'm going to say the second derivative of y with respect to x is the derivative of the function dy dx with respect to the variable that's there. I'm going to write that's going to be dy dx with respect to time, the derivative that's in that function, times dt dx. But dt dx would take some work to figure out. I already know dx dt, so instead of multiplying by dt dx, I'm going to divide by dx dt. Well, notice to take the derivative with respect to time of 1 minus 3t squared over 1 minus 2t, I need the quotient rule. So that's going to be low, 1 minus 2t, d high minus high, d low is negative 2, all over 1 minus 2t squared. And then I ran out of room to multiply by dt dx or divide by dx dt, so I'm going to move me out of the way and I'm going to divide this whole thing by dx dt, and dx dt, we already found it out, it's 1 minus 2t. So this is a fine answer for your in the free response section. I might or might not ask this free response versus multiple choice. This one here is written free response style. You'll see the next one's written multiple choice style. So you might simplify this. I'm going to write 6t minus 12t squared plus 2, that's a times a negative 2, and I see I didn't put that in parentheses, so it looked like subtraction, plus 6t squared over, this is going to be 1 minus 2t to the third power. Does anything up there simplify? I have a minus 12t squared and a plus 6t squared. So if I was going to write one more final answer, I might write this: d squared y dx squared equals, that's negative 6t squared plus 6t plus 2 all over 1 minus 2t cubed. Final answer. All right, so you tried this one from the new course exam description for this year. Here's a hint. The answer is A. All right, so new to you this year in Chapter 7, new to the BC curriculum, is different from the AB curriculum, is you learn how to find the length of a curve. So we can find the length of a curve, the length of a path traced out by a particle moving along a path defined parametrically. So you can see the similarities here. Remember that curve length formula that you learned in Chapter 7 came essentially from the Pythagorean theorem, finding the hypotenuse of the triangle when you traveled a small distance, a small x distance and a small y distance, and finding that hypotenuse and adding up all the hypotenuses. Well, here you already have x and y given differently, so we've essentially find the same thing. We're going to add up all the hypotenuses of the little triangles that your particle or whatever crosses over. So your limits are going to be the change in time. So if I care about how long the curve is traveled between time 0 and time 4, time 0 and time 4 are going to be my limits. And I'm going to, might as well do this problem here. The length of the curve determined by the equations x equals t squared and y equals t. So it's going to be the interval from 0 to 4, one big radical, and this is supposed to look like the Pythagorean theorem. Essentially the change in the x-coordinate squared plus the change in the y-coordinate. Well, change is derivative. So change in position, we have the derivative of x equals t squared is 2t, but that all has to get squared, plus the derivative of y with respect to t is 1, but that has to get squared. You could leave this answer on the free response section, but notice it's simplified to choice D here. And you can see my note at the bottom. We're going to save the really good FRQ problems for the next section, because the next section sort of combines with what we just learned here about parametrically defined equations and vector-defined equations, which in some sense are exactly the same. But we need to know the notation from the new stuff to do most of the cool free response problems.